All right, everybody, let's go ahead and carry on with our uncertainty discussion. We've already covered a lot of concepts about sources of uncertainty, how we calculate uncertainty. Now what we'll talk about is how do we sample to understand uncertainty? What's the methodology for sampling? Now, I apologize, I've got a bit of sun coming in through my front window right now, so my face is getting kind of lit up. I'm not in any way angelic or anything, but so let's go ahead and get started with this discussion. Now, in a perfect world, the way that we could solve this problem as far as understanding the uncertainty would be simply just to sample our way to it. So, how would we do that? We have some type of decision criteria. That could be the recovery factor, the flow rate, the volumetrics, the mineral grade, the amount of water in the aquifer. It's something that we're going to use to determine or to make a choice about what to do with the subsurface. Now, in a perfect world, what we could do is we could just build many equal probable models. Treat them all as equal probable. You could weight them if there's scenarios that are more likely or less likely than others. You could do some form of weighting, of course. And you could go ahead and then build those models, build M models, that's a bunch of models. For every one of them, you could run the transfer function. You could sort them based on the probability, plot them, and you would immediately have a PDF or a CDF in this case for the decision criteria that you could use to assign P10, P50, P90 to calculate the best decision in the accounting for uncertainty. That would be perfect. And we could just do that. But really, that's what we would like to do. But we got some problems we have to face. The first problem is the uncertainty space is vast. It's very, very big. Once again, imagine if you have n model choices or parameters we have to work with, and we just sample it with k layers. The result is going to be scenarios equal k to the n power. We saw previously that would be a lot of scenarios if we have a significant number of variables to work with. But then in addition to that, the total number of models is going to be equal to those scenarios multiplied by the number of realizations that we want to use. So it's a lot of models. It's very hard for us to build that. Then we also acknowledge that it's not a very good sampling anyway, because with 3 layers on each property with the curse of dimensionality, it's not an exceptional level of sampling. We haven't sampled the edges. We don't sample in between the values. We're missing a lot of information when we do it that way. So the sampling space is vast. We've got to do something about that. Now, it would not be as bad if our transfer function was super cheap, because we could just do millions of models. We could calculate them very quickly. Geostats tends to be pretty quick on reasonable sized models, and we could apply the transfer function to all of them, and we could build up a distribution and sample our way to the problem. The transfer function is often quite expensive. Flow simulation got faster every year. The models got more complicated. The flow got more complicated. More is being considered. And the result is it still takes a lot of time to do the transfer function. So we can't, these two problems, the vastness of the uncertainty space, the computational overhead of the transfer function, and the result is we have a problem. We have to do something about it. What do we do about it? The general approach is use of a response surface. What is a response surface? It's simply going to be a proxy model that provides us with an approximation of the behavior of the response in the presence of all of the possible parameters. Okay, so what are we going to do? Let me show you how we do response surface modeling. I give myself a very simple problem. We have permeability variance, and the permeability variance has some type of uncertainty distribution. There is low permeability variance, low Dijkstra-Parsons, low heterogeneity, mid and high. Low porosity average, low volume, mid and high. And the response variable we're working with right now is recovery factor. Might be recovery factor between two wells, might be recovery with a 5-spot with injectors and producers. It's recovery factor. Okay, so we're going to sample the problem. And so what we can do is we can sample the problem with 3 levels with the 2 variables. That's 9 scenarios. We'll build multiple realizations. We'll get the average recovery factor at each one of those combinations of low, high, mid, high, porosity average, and permeability variance. When we do that, what we have is we have a response surface that describes the recovery factor as a function of the 2 variables of interest. Now, if you stop there, if you said, well, I'll just take the combinations of low, mid, high, and I'll go ahead and just take that and sample that, that's my distribution of recovery factor, we would be in error. Because this low, mid, high are not really technically equally likely. If we pick the middle value, we pick the P10, they're not 1/3, 1/3, 1/3 probable. And so we would not have the right overall probability associated with the response variable. In addition, the uncertainty space is very big. We have combinations we're not sampling. Out here, in here, and here, and here. We have not sampled. So we did not consider the probability of the specific porosity and permeability combinations. We didn't consider these univariate distributions. And we did not consider extrapolation to other values away from what we sampled. So we're going to do Monte Carlo sampling to do that. What we're going to do is we're in fact going to take that response surface and treat it like a proxy for the recovery factor. And so we'll do Monte Carlo sampling from the uncertainty distribution for the mean of porosity coming from our problem, the uncertainty distribution for the variance of permeability. We do 1 Monte Carlo sample from each, we find the combination, and then we take that as one realization for recovery factor. Repeat, repeat, repeat. What are we missing? We have not accounted for the relationship between permeability, variance, and the porosity. We've assumed independence between them. To be honest, most workflows that do this, response surface Monte Carlo resampling or sampling, do not account for the M variable cross relationships. That's not modeled. We simply assume independence. In addition to that, the response surface had a specific form or features to it. It may be a model based on linear regression, which would actually result in a weighted adding of the variables, which will have an impact on the final response recovery factor distribution. So we got to be very careful about how we do all of this and be familiar with what's going on. Now, we got a sample in order to calculate that response surface. And so how are we going to sample? Now, what I've shown up until now has been just simply full combinatorial. We got 3 levels, 5 levels, 2 levels, whatever it is. We'll have k to the n, where k is the number of levels, n is the number of variables, combinations that we have to model. Now, as I mentioned before, if we're working with 10 variables, 3 levels, that gets to be a very big number. 10 realizations, it was 600,000 models we had to build. Can't do that. In practical workflows that I've observed, modeling up to 100, 500 models is probably all we can do. We're not talking about building 500,000 models. Okay, so what are we going to do? One way we can do it is we can use some type of an optimal design, and this is commonly used. And so we can go ahead and say, let's pick the combinations of the levels and variables such that we meet some type of optimal constraint. And the d-optimal approach will give you the combinations of samples you should take, and the actual sample schemes are available online for a given number of levels, for a given number of variables. It'll tell you which combinations to take so that it maximizes the determinant of the information matrix. Effectively, the fewest number of combinations required to give ourselves a pretty good understanding of what's going on. It captures as much information as possible. It's a design. Plackett-Berman is another one. There's others. They all have their assumptions. With the Plackett-Berman, we're basically trying to capture more of the direct relationships, not so much of the interdependencies between, but there's a lot of different designs that we can work with. If the design is quite sparse or efficient, and we're missing out on a lot of the complicated interactions, we could use that as a pre-screening in order to determine which variables are most important, filter out the ones that don't matter as much in that first pre-screening, and then go ahead and move forward with a more comprehensive design with the variables that matter. That would be an efficient workflow to try to get around this problem of can't work with full combinatorial. So these reduced designs are often used as the first step for screening. We might go to full combinatorial after we screen out to a few enough variables that we can actually model the combination, the full combinatorial. We will be tempted at every step to do what's known as ranking. Ranking is alluring. It's a great idea. The idea is this. Imagine if we had some fast proxy we could run on the models instead of running the full transfer function. Now, once again, if that took 1 second to run, now we're talking about a capability to, in fact, just run all the models. And we can see how they do. And so what we say is, if we had a fast proxy, it doesn't have to be accurate in as much as the absolute value of the response, but the relative value versus the other models should be pretty good. If it is, we could rank all of the models. We could run this. We have our many realizations and scenarios, and we could pre-rank them. Now, what's interesting, what would be alluring is if our rank was perfect, we get back to that idea, build many, many models, rank them, and then we could just know which one of them is the P10, the P50, the P90 result for the decision criteria, only run those through the expensive transfer function, and we would be good. Unless we have a problem with rank error. And that is, model number 1 may be identified to in fact be perhaps a P55 or 60, whatever that is right there. But in fact, there's error right here. And the truth would be, it should in fact be a P40 or P35. And you could find that model M is supposed to be down here, but they could actually start to switch around because of error. Now you can imagine if that error is significant and we just run 3 models through our flow simulation, we could find ourselves in the unhappy position where when we pick 3 models, we run them, we find out the P10 performs better than the P50 and we're confounded. And that often does happen. So ranking is alluring. It would be a beautiful shortcut. We could pick the models that have specific percentiles, only run those, and we would think our job was done, but there is ranking error. So it's dangerous. The overall methodology would be with ranking to pick those critical models, P10, P50, P90, to then have the P10, P50, P90 result for the decision criteria, hope that it's close, and then we could do some simple interpolation or CDF fitting to basically get the entire distribution, super compact, super efficient workflow that we could develop. Once again, the main problem we have, the limitation of ranking, is ranking inaccuracy. We expect to have some degree of error. You predicted it to be a P10, it may actually be the P13, the P15, or maybe even the P53 if you have a poor ranking measure. It's not a good proxy, or not a good indicator of the relative value. Now, what else is the problem? If we do ranking, it's quite a limited sampling of the decision criteria distribution. We have to make simplifying assumptions with regard to the distribution shape. We've sampled only 3, 5, limited number of percentiles, and we're going to assume something about what the distribution does in between. The distribution may be complicated. That may not be good enough. There may be extreme tail extrapolation. If you just have the P10, you've got to decide what's the low absolute minimum case. And many projects, those tails are important. That's the low side risk. That's the upside potential. And we want to understand those too. You may miss out on those low and high side cases. And finally, as I mentioned before, ranks are in fact very, very sticky. As soon as you run this ranking and you've declared that model 453 is your P10 model, I guarantee you that piece of metadata of exactly how you ranked it is going to disappear. That's your P10 model from now on. And people will apply it to brand new questions. But we must retain the ranking criteria. If the ranking was based on global oil in place, volume of water, flow rate, recovery factor, whatever it might have been, you must remember that, because we can't use that model, that rank, for any other questions. We have to re-rank if we're doing any new question or any new test on the model. Once again, not a fan of ranking, but if you're going to do it, we got to be careful about how we deal with them. Okay, so let's talk about how you'd rank. Just give you an idea, I'll give you 3 examples of potential ways that you could rank models, so it's not completely abstract to you. If you're running flow simulation, what you could do is you could use a simplified version of the flow simulation, a reduced complexity. If you have multi-phase flow with all of the complexity of the interactions between the phases, you could run it as single phase. If you're running flow simulation with typical types of approaches that solve finite element and so forth, you could go ahead and do streamline-based simulation or some other type of simplification. I've seen people use fast marching, permeability weighted distance types approaches and so forth. Now, related to that, you might want to use a geometric proxy, a connectivity metric. People will often use dynamic Lorentz coefficient. Lee and Deutsch in 2008 suggested a really nice example for primary depletion connectivity around a well based on a weighting. Now this is very interesting. What you do is you go to every well location and then you go to every cell that could potentially be connected within the radius of possible drainage of that well. You take the volume available, pore space within that, which would be, so the volume of the cell combined with the porosity gives you the pore space. You get the fluid, the amount of hydrocarbon, by removing the water saturation. And then you use 2 components. The first one, for every cell away from a well, you count for the tortuosity. How far did it have to travel, using a fast marching or something like that, and you count for the permeability. Now you could account for the permeability path and so forth using fast marching with permeability weighting and so forth, but somehow you count for how hard it is for the cell to get, for fluid at the cell to get to the well location. That would be a connectivity proxy, pretty straightforward. Volumetric calculations, very straightforward. You just go over the entire model, you go over the entire subset of the model, the radius of drainage, and you just calculate the available hydrocarbon, water, mineral, whatever it is that you're trying to assess within a specific subset of the model. Those are ranking criteria. Hope you can see that these can be calculated very quickly. Fast marching is 2 passes over the model, numerically extremely fast. Okay, expert advice is to avoid ranking if possible. So what we're saying, apply the transfer function to all models if possible. Do smart things with filtering the number of variables you're using, use a reduced design, ranking of variables, simplify the problem, hit the big hitters, get the variables that matter most, then sample them well, and avoid ranking methods. If ranking is required, procrastinate ranking to the latest possible part of the workflow. Don't rank on static and then run very few models through to dynamic. That can be very biased. Try to rank at the very last moment if possible. I know this is a huge challenge. I know it makes things harder, but early ranking often causes biases to be propagated through. So, rank as late as possible so that we don't propagate bias through, and avoid ranking if you can. Many modeling failures can be traced to the misuse of ranking. Ranking is extremely dangerous. All right, so next I'll have a lecture about summarizing over realizations. The sun effects have been kind of interesting in the room. I apologize for that. I hope it's not distracting, but it is kind of cool. The sun is rising. My window in my office faces east. Has a nice view in the hill country. I do enjoy that. But so, in general, I hope this was useful to you. I'm Michael Perch. I'm an associate professor at the University of Texas at Austin. I am the Geostat guy on Twitter and on YouTube and GitHub. And I hope that this was useful. If you have any questions or comments, drop me an email. I usually try to be pretty responsive, although I've been pretty busy these days, but I try my best. All right, take care.